my name is Lukas. I'm a PhD student with Matthias Niesner at the TU Munich and happy to give him the chance to talk about my research, which is about generating navigable 3D scenes. One could also say I'm talking about world models, which is a pretty hyped up term these days in the field. So maybe to clarify what I mean with that, I'm interested in creating digital 3D environments that look and behave like the physical world. So here are two examples. These are 3D scenes that we generate, and you can walk around them, you can look at them from different perspectives, and they look hopefully the same to you as any arbitrary scene that you walk around in might look like. And let's maybe get started. Why is this interesting? If you wanted to generate such a scene by hand, it's actually quite complicated. Like here's a video of somebody designing a bedroom scene in Blender manually. And as you can see, it requires a lot of expertise and manual steps to craft the object furniture exactly like you want it. It can take several hours, and it's still only a very small chunk with like a bed and like a small shelf, and it's already quite complicated. On the other side, we have very strong generative models like Stable Diffusion or Sora, or nowadays there are even more image and video models that can generate high quality and diverse images from just a text prompt as input. And this is a very easy to give input, like almost everybody can write a text prompt that describes something and the AI will generate it. So the question naturally becomes, is it possible to leverage these 2D prior world models to generate 3D scenes automatically without requiring much expertise? And this is what my research is about, and I'm also talking about this blue box basically during this talk. And why is it a good idea to know how to do this? I give credit to a startup called World Labs. They basically are doing something like this as well, and they have shown some industry pitches why creating 3D scenes is good. For example, if you want to train robots, you need to train them in diverse environments, but it's super hard to capture real-world 3D scenes. We also have only a few thousand high-quality synthetic scenes, and if you could just generate them automatically, you can train your robots in much more diverse data, and hopefully they work much better then. Or another pitch is to use these scenes for VR, for gaming, for movies, to walk around in them, maybe have somebody shoot a gun at like the furniture or so, whatever you can imagine basically. And the third application might be digital twinning, where you take a bunch of photos of your living room, it gets digitized in 3D, and then you can look at it, how it looks like with a different wall color, or if you would remove the table or replace it with something else. And now I want to get into the details of the research. I will start with two very brief overviews of earlier papers that laid some of the foundations for this, and then go into more depth in two of our recent papers. And I'm going to start with Texture Room. This is a model that generates textured 3D meshes from a text prompt as input, as you can see here. And it was among the first to showcase that it's actually possible to leverage these 2D models to generate 3D scenes. And it is a pretty simple idea. You just start with a single image that you generate from a text description, and you estimate its depth with an off-the-shelf monocular depth estimator. And this already gives you the opportunity to triangulate, unproject, and create a scene patch. And the idea of this method is now to iterate this principle multiple times, where you start off from a current scene patch on the top left, and you render it from a novel perspective into a viewpoint that doesn't show content everywhere, and you in-paint the missing pixels with these 2D models. And you generate what the scene to the right would look like, basically. And again, you estimate the depth of that newly generated image. You have to make sure that the estimated depth aligns smoothly with the known depth, such that you have continuous alignment between the two images. And then you can just unproject again, and you obtain a larger patch. And if you do this 100 times from different perspectives, it would look something like this. where on the left you see how the scene is iteratively built up, and on the right what the frames are looking like that we generated from different perspectives. And you can see that the scene gradually is complete. It has walls, it has floors and ceilings and multiple different objects. And here is a fly-through that we can render from that. And you can see the textures are quite compelling. There's a lot of intricate detail. And this is how the geometry also looks like. And in a second, the camera will fly out, and then you can see that it's actually a watertight mesh with walls, floors, and ceilings. But if you look more closely, you can definitely spot some problems. Like this geometry here looks pretty distorted, right? It doesn't look like a table would usually look like. From the front, it looks quite good, but from the side, doesn't. And the problem is with this first approach, it was a pretty naive frame-by-frame generation. And if one frame has a wrong depth estimation, or you generate something that doesn't look quite good, then you're basically doomed and cannot replace it. So we figured out that a key missing ingredient was multi-view generation, meaning that we want to train a diffusion model that doesn't generate a single image at once, but it generates multiple images at the same time from different perspectives. And if you have such a model, then all of a sudden these stretched out artifacts are gone because you are constraining how the geometry looks like from different perspectives all at once. And this is what we explore in the second work, ViewDiff, which is actually one I presented in my first time being here. So I'm also keeping it a bit shorter, just as an introduction sake of View. The way this works is to fine-tune an existing text-to-image model. So we use stable diffusion, which is a unit architecture, which takes as input a noisy image, and it predicts the noise applied to it. If we now want to generate multiple images at the same time, we are extending this to generate multiple images, and we give additionally the camera, the relative camera between them as input. And we enlarge the unit architecture in two ways. We have this yellow box, the cross-frame attention, which enables communication between the two images. Basically, they can share each other the features that they use to generate the image. And we also have a projection layer that works as follows. We have two input features, and we know their camera viewpoints, and then we can unproject the pixels into a 3D voxel grid and aggregate them with a weighted mean. And we have some CNN layers that iterate on top of it, and we render down, again, 2D features from this unified 3D grid into 2D output features. And by design, this ensures that the features that the unit is operating on are 3D consistent because they come from the same 3D voxel grid. And what this gives us is the opportunity to train this model on 3D datasets. We use object scale datasets from the Co3D dataset to denoise multiple images at the same time. And what can we do with this? This is an example of, given a single input image, we generate more views around the scene. And the baseline methods actually are 3D methods that render down images, whereas ours only generates the images in a 3D consistent fashion. And you can see that since ours is a 2D image model, the quality, like the sharpness is higher and the background is also sharper. And even though it's not a 3D model, we are already able to generate quite consistent 3D frames. And this enables a key ingredient that we leverage later for the scene generation, which is autoregressiveness. This means that if we have such a model, we can generate multiple images at the same time, and then we can just reconstruct these images into a 3D model by 3D reconstruction, like NeurIPS or Gaussian splatting or whatever is fancy these days. And then we can render this model from a novel perspective and condition the 2D model on those renderings to generate new views from more perspectives. And this is like an autoregressive generation reconstruction loop that we use later as well. And we kind of demonstrate it here, where we show in this video how multiple images are generated in batches. So each of these images that appear on the left depict one sequence of frames we generate. And in total, over 100 frames can be generated in a consistent fashion in this way. And this turns out to be the missing ingredient to make 3D scene generation much better. However, one component was still missing, which is scene scale multi-view generation. So our approach was trained on object scale data, but in order to generate indoor or outdoor scenes, it needs to be a model that is trained on such arbitrary data. And nowadays, video diffusion models are uprising. And in particular, there are some that generate videos while being conditioned on the cameras. And for example, this work, stable virtual camera, takes as input a blue camera trajectory that specifies how the camera should move and the input views of the scene. And then it can generate these output video sequences. And this turns out to be like a generalization of the earlier work to arbitrary scenes. And in our next work that I now want to go into deeper depth, technically, we show how we can leverage such models to now generate entire scenes in a more 3D consistent fashion. And this is a World Explorer work that was published last year at SIGGRAPH Asia. And it's again a method that generates 3D scenes from a text description without requiring any expertise as input, other than specifying how the scene should look like. And this is an example rendering through the scene. And what I want to focus on is how much the camera can now move around furniture. So in previous works, there were already some distortions visible, but now the camera can move around freely throughout the scene without much distortions. And we base this approach on 3D Gaussian splatting, which is the overlay that you're seeing now. So these are the individual Gaussians visualized that make up the scene, and we can render them into these photorealistic renderings and really explore the scene. And this method is decomposed into 3 stages. Panorama initialization, which defines a rough scaffold of how the scene should look like. Then we expand this scaffold with a video diffusion model that generates multiple videos that explore the scene along different paths. And then finally, we reconstruct the scene by running Gaussian splatting on all the generated frames. Let's dive deeper into the first part. So panorama initialization works as follows. We are given a style prompt. For example, all frames should look like a honeycomb observatory. And then we specify different subtypes for each frame. For example, the top left is a bedroom in this style, the top right is a living room in this style, and so on. Then we have 4 images, and we just define that they are rotated 90 degrees around the scene origin. So they look like shown here in the middle. And if we run depth estimation on each of them, we get these partial point clouds that are not overlapping and is like the first part of the panorama. Now we leverage again the same technique as in the texture room work, where we render the input point cloud from novel perspectives that are 45 degrees rotated and are 4 other views. So you can see in the middle top the renderings of the point clouds from these 4 perspectives. And then we again leverage 2D models to inpaint the missing white regions around them. And finally, we obtain this panorama that is now showing how the scene should look like from the scene origin. However, only these 8 images don't really resolve any occlusions or show the scene from much deeper depth. So the next step is really the key ingredient for this paper, which now utilizes predefined trajectories to expand the scene. So here we specify one example trajectory that starts off from one of those 8 images and just moves forward. Here's another one that is a bit more interesting. It moves forward, rotates to the left, and then moves backwards a bit. And the key idea that we propose in this paper is a scene memory mechanism where each trajectory is conditioned on the previous frames. So if this is maybe the 10th trajectory that we generate, we save all the previous frames that we created, and we select the 5 frames that are most relevant to this trajectory based on like camera viewpoint similarity, and condition the model on those. Exactly the same way as this autoregressive generation worked in the earlier ViewDiff work. And this way, we can generate multiple videos in a 3D consistent fashion depicting the same scene just from different perspectives. Here's another example video of another trajectory now looking to the right. And there's one more important ingredient. This is necessary because our trajectories are predefined, but we don't know what the model will generate. So it can happen that the camera moves too far into the scene and might collide with a wall or furniture. So we also have a collision detection mechanism that is pretty simple. It just looks if the depth to the generated frames is too small, then we just stop the generation earlier, and then we don't run into any walls. And if we completed that, then we get around 1,000 frames that are oriented around these trajectories that you see in the top left. And they show the scene from many different angles. And now we want to reconstruct the scene in 3D. And we use Gaussian splatting to do that. And in order to do Gaussian splatting, we first need a point cloud as input. And we run off-the-shelf method called VGGT. Maybe some of you have heard about it. It takes as input the images, and it outputs you the point cloud. And this is shown on the top right. And then this is the initialization for Gaussian splatting. And Gaussian splatting then uses the frames from the point cloud initialization to refine per point Gaussian blobs that have a color, opacity, and so on, and can be rendered into photorealistic images. And yeah, here we visualize the optimization. You can see it converges quite fast because the point cloud initialization is quite dense. And scenes that we generate look like this. These are two examples. You can get pretty creative with the prompts, which is super rewarding once it works, because you can also generate pretty fancy things, like the left scene with liquid metal floors looks quite unusual maybe. But still, you can walk around the scene pretty much. Like, these are renderings from the 3D Gaussian splatting scene, and you can see the camera can really go into detail and look around furniture quite a lot. And in comparison to baselines, this was a huge step forward. So here's a maybe pretty hard to see video, but all the baselines to the left, they cannot really show the scene too much from different perspectives. Like, they all look quite decent if you are around the center of the scene, but as soon as you would walk towards the walls or rotate too much around objects, it would distort and stretch, just in the way that this texturing method did in the beginning. And in contrast, this method was able to resolve these issues quite nicely. However, there's still one important thing that we didn't like about the approach, and that is the 3D consistency of the generated frames. We are using a video diffusion model, which is a probabilistic generative model, so it's pretty hard to get them to a point where they generate frames that are perfectly 3D consistent. With 3D consistent, I mean if you have, for example, this kitchen table here in this top left image, if you rotate the camera, you want it to be exactly at the same space in 3D. And if it's not, then the 3D reconstruction will break. And that's actually what we see with our approach. So if we render the 3D scene from World Explorer that we reconstructed for this scene, and we rotate around this table, we can still see some floating artifacts that don't look super compelling and realistic. And this is not because we didn't see the table from those perspectives, but actually because the generated frames are not consistent. And you can see this in the right, where we run a method that reconstructs a 3D point cloud geometry per frame. And as you can maybe see, is that the tables don't align. So hopefully you can see that there are multiple surfaces of this front shelf of the table, and they are not all in the same 3D position. And if you now imagine you run a 3D reconstruction on this input, of course you will not get a good looking geometry, so that explains why these floating artifacts occur. Our latest archive work from this year tackles this problem. It's still using the same kind of architecture where you're given a text prompt as input, a diffusion model generates a bunch of frames, but now we acknowledge that these frames are inconsistent and have problems that we cannot just ignore and reconstruct right away. Instead, we propose a new method that fixes these alignment problems to obtain a consistent 3D world. And this is a small peek how these worlds look like. This is now a sharp rendering without floating artifacts. And in comparison, this is how it would look like if we didn't handle the inconsistencies, like just run Gaussian splatting on the frames. And as you can see, these blurriness, floating artifacts are gone now with this new approach. And yeah, we were quite excited about this because for the first time, we're now able to generate 3D scenes that you can explore from arbitrary perspectives, and it doesn't break from certain angles. So this is the last work that I'm talking about. How does it work? We start off with the frames that we generate in the top left, and we again run a method that predicts the geometry. This time it's the follow-up from VGGT. It's called depthAnything3, and it predicts you the depth maps and the camera positions of the input frames. And if you naively unproject this input, you can immediately see what's wrong with the frames. For example, here you have this open surface in the kitchen, appears 2 times and is not aligned. And this is exactly what's wrong with the input frames and exactly what we want to fix. So how do we fix it? Turns out there's a pretty simple way to fix it. There is a method called ICP, which is pretty well researched in the last decade. And what it does is it aligns 2 point clouds to match surfaces. And this is exactly what we need to resolve these issues where the ovens don't align. So what we're doing is all the frames that we generated, frame by frame, we go through them and we align each frame to the current model, where we not use rigid ICP, but one important ingredient is that it's non-rigid ICP, where it allows each point cloud to transform non-rigidly to match the surface geometry that we have collected so far. And we can visualize this on the left, where orange is the point cloud before alignment, and you can see it's off, and now it's moved in green towards the existing surface. And we iterate this over all the frames that we generate, and eventually we have a point cloud that now doesn't have these misalignments anymore. And this point cloud is now the improved starting point of our 3D Gaussian splatting reconstruction. And there's one important ingredient, like this is maybe the key component of this entire method, is that we now have this point cloud initialization, and we apply a backward deformation that undoes this alignment back into the inconsistent space. And then we render the Gaussian scene from the input camera and make it similar to the video diffusion frame. And this optimization can backpropagate through the deformation and optimize the Gaussians in their consistent space while being optimized from the inconsistent frames. So this is also why it explains the paper title. We can generate 3D scenes, we can reconstruct worlds from inconsistent views in this way. And we still have quite fast convergence in only a few thousand iterations of Gaussian splatting optimization. And we compare this in 2 setups. We can use an arbitrary video diffusion model, like this time I'm using ViewCrafter instead of Stable Virtual Camera. And this is a video that starts from this frame and it tilts the camera a bit downwards. And we compare against different methods that reconstruct this 3D scene. And ours in the bottom right shows the fewest floating artifacts, which showcases that we are able to resolve these inconsistencies that are visible in the input frames. This is another example of a single video sequence where we also see quite some nice improvements. And this method really shines if we now plug it into our previous World Explorer work, where we just take all of the 1,000 frames that we generated and reconstruct the scene. And here we can see, in comparison to the baseline methods, that we really have sharper details. Like if you zoom in on certain areas, you can see floating artifacts in the other works, but not in this work. And here's another example of this honeycomb scene that we have seen a bunch of times now. All right, so I hope I could convince you that these scenes are indeed looking pretty nice 3D consistently. If I couldn't convince you, then I invite you to scan this QR code and play around with the online viewer of a scene that we have. Then you can select your own camera viewpoints of a scene and it should work on a smartphone, but in all fairness, it's like 80 megabytes, so consider it with your data. And then you can walk around the 3D scene freely, whatever way you want. And here's an example of a screen recording that I did, where we're just walking around the scene with the mouse and keyboard. It also works with touch controls. Yeah. That's the end of my talk. So I hope I could convince you about 3D scene generation being an important subject. And it was my pleasure to share my research with you. And yeah, would be happy to answer any questions now. Thank you.